Okay, now let's talk about the fully implicit method. So you can notice that if you compare with the explicit method in our previous slides, you can notice the difference here is we are actually evaluating the right hand side at the next time step m plus 1 instead of m. Because if we put here m, then basically we are directly going forward in time. But in this case, since the right hand side includes the terms with time step n plus 1, we cannot get the value of the next time step explicitly. But we can only actually consider the now these 3 points here. So this is actually our u and m, which we already have on the right hand side. And actually we are going forward in time and we are trying to obtain these 3 values. So this is n minus 1, m plus 1, un m plus 1, um plus 1. You can see this is also m plus 1. So this is our stencil, and you can compare in the explicit method. Our stencil was different. So we had these 3 points, and using these points at n minus 1 m, we were obtaining the next time step explicitly. So these 3 points, if we combine this weighted average of these 3, and then we can get directly the next time step. So this was the stencil in the explicit method, and now this is the stencil in the implicit method that we are discussing. So the advantage in the implicit method is that basically we don't need to have the stability condition, so we don't have such restriction anymore. But the trade-off is, of course, we need to basically solve a equation system at each time step in order to get these values at n plus 1. So that's the trade-off. And we can represent this in a matrix notation as usual, just like the explicit method. And notice that here our coefficients here is minus alpha, 1 plus 2 alpha, and minus alpha. So these are gonna show up here and here. So you can see we have again a 3-diagonal coefficient matrix M times the next time step m plus 1, and again going back here. So this is now written as a vector, these terms. And on the right hand side we have the time step m, so that is here, okay? And basically we have these boundary conditions which are added separately, again just like in the explicit scheme. And one more time, notice that we have n minus 1 times n minus 1 matrix of these 3 diagonal terms. And basically the right hand side is represented as these b vector, okay? So if we write this in a even more compact form, basically we have this 3-diagonal matrix M and the vector of unknowns, and what we already know is on the right hand side given by this B. So the solution can be computed by M inverse times B, and if we do this at each time step, we can go forward in time and basically complete the whole solution can be computed. However, you can notice that we don't want to, especially if we have a large matrix, we don't want to do this inverse operation, which is computationally expensive operation. And therefore, you can consider to use the LU decomposition. And basically in MATLAB, you can remember to use the backslash operator for performing the Gaussian elimination with these LU decomposition. Okay, so next we will discuss Crank-Nicolson. Basically in Crank-Nicolson we will be combining, or in other words, we will be averaging over the explicit and implicit methods together to take advantage of both of these methods.